Morning, folks. Hey, listen, registration is starting up really soon. Registration is, I think it starts tomorrow. Is that right? At least for some of you. What's that? Oh, they haven't changed that yet? It's ridiculous. Who's up at midnight, for goodness sake? Are you a lot of it? Really? They should change it to like 7 a.m. or something. Or maybe that'd be more difficult. Hey, David. What? Listen, you're going to find with the labs that they're going to fill up pretty quickly, so please register for those early uh, to just forego any issues. Listen, it'll seem always that like we're don't have enough spots, but we always have enough spots for the lab. If we need to, we'll add another section. Likely that will happen. I'm not sure when that's going to be, but go ahead and try to get registered now if you can fit it in your schedule. Okay, so there might be the option of adding another section later, but it's probably going to be Friday afternoon, which doesn't help you. Would that help you? Okay. Also, there is the MCAT class. That is a physical science class. We have a few pre-med students, right? Just a few. But that MCAT class covers physics, organic, and general chemistry. And it's a physical science 301 class. If you're a biology major, that counts as 2 hours of your electives. It is a pass-fail course, so you get either like a P or an F. So it doesn't affect your GPA, but it will go towards your total number of hours if you're a biology major, towards your electives, your biology electives. All right. Um, let's see. Other notes. I'm going to get out today or tomorrow. I'm working on it. Your take home for the derivation and your take home for this next chapter on statics and equilibrium. That chapter is going to be pretty short. It's really not new material. It's just sort of new ways of applying that material. And we'll work through some example problems, and then I'll give you one or two take-home problems to do for the exam. The derivation that we'll do, and I'll send it out later, it's going to be a bar that's rotating. We've already done a bar that's rotating about its central axis, but instead I'm going to do it rotating about the end axis. The derivation is very similar. It's just sort of changing the limits of integration a little bit different. Okay? You can find it online. I just really want you to go through the process of deriving that and put it on paper. Alrighty? I'll send that out today or tomorrow, as well as the take home for the next chapter, which we're not going to get to today, maybe next time, maybe Monday. Alrighty? We have one more chapter after that. I know it's not in your book, but I've just added it because Dr. Balaji wanted me to add it on optics. It's going to be ray optics, ray tracing optics. We'll look at lenses, mirrors, the lens equation. Nothing too terribly complicated. They're really just sort of some simple rules that you follow, but you'll need to know how to trace light through lenses and mirrors and know how to solve for magnification, image distance, object distance, stuff like that. It used to be a topic that we had in the second semester, but the state sort of reorganized how we teach this course, and so it just sort of fell out. It actually goes into a third semester of physics, which we don't offer here. Okay? Have any questions about what's coming up? No? All right, we're getting close to the end, right? We have this week, next week, and then the following week. And that following week is probably going to be a doozy for some of you. I know that a lot of you probably have exams on that week. So make sure that you're planning ahead right now, that you're preparing for stuff. Why don't we get that take-home test out early so you can go and start on that and hopefully get it done in the next week or so. All right? All right, let's see where we leave off last time. We had just covered moments of inertia, went through all those derivations. Again, if you didn't really get the derivations, don't sweat it too much, but I do want you to step through that derivation for the take-home, and then we'll sort of call that a done deal. You won't get to this until Calc 2 or 3, but hopefully you'll remember a little bit of it when you get to it in that class. It's really the process that I want you to be familiar with, how to integrate over surfaces and through volumes. Um, we'll do that some more next semester when we get into gravitational fields. You will have this table for the upcoming exam. It's on your equation sheet, which is online. This table just shows the moments of inertia for different objects. We derived this one, we derived this one, we derived this one, and we derived this one. As I said, for the take-home, you'll need to derive it rotating about the end axis, not where the axis of rotation is through the center. Um, if you have more than one object that is rotating, then to find the total moment of inertia, they just add up. It's a lot like mass, right? If you have more than one object that has mass, you want to know the total inertia, you just add up the mass. So it's a scalar quantity. You just add it up if you have more than one object. So, like for example, let's look at this clip. This is from the toy. Uh, oh, yes, I wrote the Toy Story. It's not the Toy Story. It's the toy. You ever seen the toy? You have seen it? Yeah, it's with Richard Pryor. He's kind of a vulgar comedian, but I think he's a really good comedian from the 1980s, 70s, I guess. But this is a movie called The Toy, and in this, he finds a Wonder Wheel. He's like a security guard at a toy store, and he finds this Wonder Wheel and he rotates through it. Anyway, let's watch it, and I want to know what is the total moment of inertia for him as he rotates through on this one. So I want to know what is his total moment of inertia. Well, as he rotates through, you basically have two parts to this system. You have Richard Pryor, and then you have the Wonder Wheel itself. And so we can approximate those as a couple of different things. Okay, James? All right. The Wonder Wheel is, of course, it's just a big hoop, and we know the moment of inertia for that is just mr squared. And then we can treat Richard Pryor as a cylinder with his rotation axis through a center. So he's rotating through this point. We'll just treat him like a cylinder. He's basically a cylinder, sort of a flattened cylinder. Um, and then we can make some approximations about both of those. Um, Let's see. Let's say, well, we know that the hoop is mr squared. The cylinder, if we look at our table, the cylinder rotating through that axis, so imagine this is Richard Pryor. Uh, it's 1/4 mr squared plus 1/12 mv squared. So that's going to be our two components. And so we'll just calculate the moment of inertia for both of those, and we'll just add them up. So let's see. It's like I skip pages here. Um, we'll assume for the hoop that it's about a mass of, say, 10 kilograms times a radius. What's the radius of that hoop, roughly? About what? No, no. It's the diameter is about 2.5 meters. Yeah, so we'll just say that the radius is about 1 meter because Richard Pryor is about 2 meters tall. So we'll say that it has a radius of 1 meter, just to keep the numbers simple. So that gives us 10 kilogram meters squared here. And then for the cylinder, uh, well, that would be for Richard Pryor. Let's see, what did I use for him? Looks like I used 100 kilograms. That's kind of big, but just to keep the numbers easy, say that his mass is about 100 kilograms. His radius, now be careful here because this isn't his radius like half of his rotate halfway from it, not like half his height, but it's the radius of the cylinder. So from here to here. If you look at your table there, it shows you that radius, I think. No, it doesn't. The radius is the distance from here to here. And then the length is the total height of Richard Pryor. So for the radius, I used a 30 centimeters, 0.3 meters. That's the distance from the middle of your chest out to the end of your shoulder. That's roughly about 30 centimeters. And then I have 1/12 m, which is 100 kilograms. That's the mass of our cylinder, or the mass of Richard Pryor. And then b is the total length. So we'll say that's 2 meters squared. And then if I calculate this, I get 36 kilogram meters squared. Right, and if I add those together, his total moment of inertia is equal to 10 plus 36 equals 46. But the point here is that if I want to find the moment of inertia of a system that has two separate components, Then I'll just add up those moments of inertia. Calculate them separately for each part and add up their moments of inertia. We'll see that come into play later when we get into conservation of angular momentum, where I have two objects that are coming together and they start rotating at the same rate. So to find the total moment of inertia, I just add up the separate components. Let's try this quick test. Here I have some discrete particles. Remember, with these, you add up the separate moments of inertia. In this, they're separated by massless rods, and each of these rods is 1 meter in length. So they're on the vertices of a square, and it's rotating about this axis. So let's calculate the moment of inertia for this system. Each of them has a mass of 1 kilogram. If you finish that one, go ahead and start on this problem, where what is the moment of inertia for this object, or if it's rotating about the red dashed line. But for now, we're just looking at it rotating about this black line through the center. All right, I'll stop at 230, 230. Okay, looks like we're sort of all over the board. Um, D is the right answer. Remember, for our moment of inertia, my moment of inertia is the sum of mr squared. Right? This is sort of our basic definition. We wrote that we rewrote this slightly differently when we said that I is the integral of r squared dm, but these are effectively the same statements. We're just writing them a little bit differently. But here, when we're working with discrete particles, I just add up m times r squared for each of the particles. Now here, r doesn't refer to the radius of the object, because the object is just a discrete particle. It's really sort of a point mass. But r refers to the distance of the particle to the axis of rotation. So here my axis of rotation is this black line. So the distance to the axis of rotation is this distance, which is 0.5 meters. So what you want to do is you take the moment of inertia for this first particle, which is going to be 1 kilogram times 0.5 squared. That's going to be 0.5 squared, which is a half squared, that's a quarter. So this will be, the moment of inertia for this will be 0.25. What will the moment of inertia for this object be? Also 0.25. It's 1 kilogram at a half a meter, 1 kilogram at a half a meter, 1 kilogram at a half a meter. So all of them have a moment of inertia of 0.25 kilogram meter squared. So the total moment of inertia will be 0.25 times 4, which is equal to 1. So D is the right answer. Now, what if I have, instead of rotating about that black axis, I have it rotating about this red dashed line? In that case, I have uh, how many particles contributing to the moment of inertia? I just have two. Because for two of the particles, this one and this one, they still have a mass, but R for these two particles is 0 because they're on the axis of rotation. Remember, R is the distance of the object to the axis of rotation. So when I have an object that's on the axis of rotation, its contribution to the moment of inertia is 0. So both of these have a moment of inertia equal to 0. And then I want to know the distance from the axis of rotation to the particle. Now, how am I going to get that? I think. Right. Yeah, so recognize that I have a triangle here. I have this triangle, which is also the same as this triangle right here. Actually, I'll just draw that triangle. So I have this triangle here, here, and here. And if I find the hypotenuse of that triangle, which has sides 1 and 1, the hypotenuse is then is square root of 1 squared plus 1 squared, or square root of 2. Then that's going to be the distance. So to find the moment of inertia for this particle, it will be 1 kilogram times square root of 2 over 2 squared. So that's going to be 2 over 4 is a half. Is that right? Yeah, so that moment of inertia will be half. Oh, and it's the same, actually. And then this moment of inertia also be a half. Is that right? Yeah. Okay, yeah, so the moment of inertia also here, if I have it go down the red axis, it's going to be the same. I could also have it go through an axis through the that comes out of the page. All right, so I have a triangle here. I know that the distance from here to here is half the total distance of the hypotenuse. You follow me? The hypotenuse on this triangle, the legs are 1 and 1, so this is the square root of 1 squared plus 1 squared, or the square root of 2. And so since this line splits the hypotenuse, this is square root of 2 over 2. This is also square root of 2 over 2. Is that clear? All right. I could also have it so that I'm going through an axis that is at the center. So now this thing rotates not like this, but it's going to rotate like this or like this. It sort of rotates in the plane of the page. Why don't you try finding the moment of inertia of that configuration? Let's see, one of these answers is the right answer, so let's try it out. What is the configuration there? Or what is the moment of inertia for that configuration? So again, it's rotating like this in the plane of the page about an axis at this point that comes out of the page. So your rotation axis here comes out of the page towards you, or into the page, however you want to think about it. All right, looking pretty good so far. Many of you have the right answer. I'm going to stop at 50 seconds. 50? Okay, let's see. A here is the right answer. Here I have four objects. They all contribute to the moment of inertia. I have this object, which is a distance square root of 2 over 2. It's the same distance that we found before, right? Half that hypotenuse. And it has a mass of 1 kilogram. So look, it's actually has a moment of inertia of a half, just like it did before, because that distance is still the same. So I have a half kilogram meter squared for this object. What is the moment of inertia for this object? It's going to be the same. They're all equidistant from the axis of rotation, half and half. Right, so the moment of inertia is the same for all four particles. So the total moment of inertia will be 4 times a half, which is going to be A, 2 kilogram meters squared. All right. You will need to find the moment of inertia for a system. You'll have a discrete particle system like this, and then you'll also have rigid bodies. We'll do a rigid body problem soon. It might be next, actually. No, we're going to do Newton's second law. Wrapped up in Newton's second law will be finding the moment of inertia for a rigid body, as with angular momentum, which we'll see at the very end of this chapter. So if you remember, the Newton's second law was F equals ma. Uh, this law also applies in circular motion, and where we're going to replace our inertia with something else and our acceleration with something else. So we're making this transition from linear motion to circular motion. Now remember, sort of our analog to mass in circular motion is what? The what? Oh, when we're moving from linear to circular motion, we're moving, like for example, we went from distance to theta, v to omega. We're going from mass to what? Inertia, right. Mass is inertia. It's a measure of inertia. So we'll go from mass to the moment of inertia, which is a measure of our inertia in a rotational motion. So the moment of inertia, that's I, is a measure of the object's inertia, and the angular acceleration, remember this was alpha, is the rotational acceleration. It shouldn't be a big step then to show that the Newton's second law will be equal to I times alpha. Well, what is it that's equal to I times alpha? What is our equivalent to the force in our rotational frame? Torque, right. So here, when we rewrite Newton's second law, we're now going to write torque is equal to I times alpha. Torque is a vector quantity. Alpha is also a vector quantity. Okay, so this is our rewriting of Newton's second law. Torque equals I alpha. I think you have this on your equation sheet. Let me double check that. Yeah, so if you look here on your equation sheet, your net torque, that means the sum of all of your torques is equal to the mass times acceleration. And we'll see some similar problems related to that are similar to ones that we did in chapter 4. Also, don't forget that torques in the counterclockwise direction are considered to be positive, and those in the clockwise direction are considered to be negative. This will be important because when we look at a system that have a bunch of torques or forces acting upon it, we'll need to know the net torque. In order to find the net torque, we have to add up all those appropriately. So remembering that net torque is equal to the sum of all of our torques. Torque 1 plus torque 2 plus however many torques we have. We did that before early in this chapter, and that's why, because when we apply Newton's second law, we'll need to figure out what is the net torque, and that's just the sum of all the torques. But when you add them up, you need to make sure that you're getting the positive or negative signs correct. That'll be good for next chapter too when we get into statics and equilibrium. We'll see sort of all this again, but in a slightly different context. All right, let's look at an example. I have this object. It's a disk. Let's see, I don't give you the mass or radius. Whoops. I'll give you the radius, but let's just say that the mass is 1 kilogram. Just keep the numbers nice and simple. And I just want to know what is its angular acceleration. So a couple things I'll need to do here. I need to find out what is the net torque. We've done that already. I just calculate the torque due to force 2 the torque due to force 1, and then I add them up appropriately, given the right sign. So our first step, calculate the net torque, the sum of all the torques. Our next step will be to calculate the moment of inertia. The moment of inertia we'll be able to find. It's a disk. We know that we can just look on our table, and that's going to be the entry for a cylinder. Remember, a cylinder is a disk, so don't forget that on your test, that if you see a disk, it's really just a flat cylinder. So we'll calculate the moment of inertia for a cylinder, and then the third step will be to apply Newton's second law. And calculate alpha. Alpha then will be torque over my moment of inertia. So let's go through each of those. I want to find my net torque. I want to calculate the moment of inertia of a cylinder and apply the second law, and then I'll have my angular acceleration. All right, so let's do torque 1 first. The torque is RF sine theta. The distance from here to where the force is applied is 1 meter. The force is 1 Newton, and the sine of the angle between them, in this case, is 90 degrees. So this just goes away to become 1. Is this torque positive or negative? The torque due to force 1. Is it positive or negative? Now really what I'm asking is, does this force cause a counterclockwise motion? If it does, it's positive. Or does this force cause a clockwise motion? If it does, it's negative. I always think, well, if I have a disc like this, I look at it and I ask, well, if I push up in this direction, it's going to cause it to move in this direction. What is that, clockwise or counterclockwise? It's counterclockwise. So this is a positive or negative torque? Right, so this is a positive torque. So it's going to be positive 1 Newton meter. And then you can probably tell right off then what is torque 2. It's going to be negative 2 Newton meters because you still have 1 meter for R. Now you have 2 newtons. You still have sine of 90, which is 1. But it is causing a clockwise motion, so it's going to be a negative 2 Newton meters. When I do that, the net torque will be torque 1 plus torque 2, which is going to be 1 minus 2, or negative 1 Newton meter. That means it's going to feel a torque in the clockwise direction. So you should always not just give the sign, but also say, well, this is in the clockwise direction. The direction of the rotation is in the clockwise direction. All right, now I also want to know what is the moment of inertia. So this is our first step, finding the net torque. The second step is to find the moment of inertia. For a cylinder, it's 1/2 mr squared. To find that, you would go back up to your table, or your table's on your equation sheet. I would say, well, I'm dealing with a disk. That's going to be a cylinder, and so I'm limited to these two options. But it's rotating about an axis through the center, so it's going to be this. So just make sure that you're familiar with that table and that you're able to give it a shape, whether it's a cylinder or a sphere or a hoop or a rod or whatever it happens to be, that you're able to pick out the right one. And you'll see different shapes on the homework and on the old test. Just make sure that you're familiar with it. So our cylinder has a moment of inertia of 1/2 mr squared. Mass was 1, radius was 1. So this is 1/2 1 times 1. So it's 1/2 kilogram meter squared. Right, and then the third step, final step, is to find alpha. Alpha is equal to the torque over the moment of inertia. It's going to be 1 Newton meter over 1/2 kilogram meter squared. Now I'm going to leave off the negative right now. We can put the negative in there. but I'm just going to remember that it's in the clockwise direction. So you can leave it there if you want. Is going to be 2 radians per second squared. You can go through the units if you want, and you'll see that you are left with just a 1 over a second squared. Uh, so it's 2 radians per second squared, and because it is negative, it's going to be clockwise direction. I'll ask you explicitly what is the magnitude and the direction. This is a really simple one. The numbers are all really easy. Yours will be a little more complicated. I'll show you an example of what to expect for the test. I think next. Alrighty, so 3 steps. Finding the net torque. We've done that already, like with the bars and finding the net torque. I do want to remind you, though, that just because our object has a radius of 1 meter doesn't mean that our force has to be applied at 1 meter. So, for example, I could have had a force that is applied right here, say like that, a force that is at an angle of, say, 30 degrees from the uh, from the object, and then you would have to find, and at a distance of 0.5 meters, and then your torque would look a little differently, right? It would be your force, whatever that is, times your 0.5 meters times the sine of 30 degrees. Just sort of play that by ear and look at it as you see it in the problems um, for calculating the net torque. Make sure you got your signs right on the torque. If it's clockwise, it's negative. If it's counterclockwise, it's positive, and you add them up appropriately. And then you find the moments of inertia using that table that I'll provide to you, and then use Newton's second law to find the acceleration. Now from there, we can go into a variety of different things like using those kinematics equations to tell me how far does it go in a certain amount of time, or what is its velocity after a certain amount of time. We've done those types of kinematics problems already, but you could see them all sort of mashed together in something like this. You likely will see that. Definitely have a Newton's second law problem on the next test, okay? It'll be using this technique and this method. Let's try this one as a quick test. Find the net torque, find the moment of inertia, and find the acceleration. And then here I'm also asking you to find the angular speed. So a lot of the same that we did already, you just have one extra step there at the end, finding that angular speed. I'll remind you your kinematics equations up here. I'm going to skip down for just a second. I'll come right back to this. Doing well so far. folks. Let's do about 15 more seconds or so. I'll stop at 3:15, 3:15, 10 more seconds. Just guess if you're not sure. I think A is right. Let's see. Some of you put C. I think I know what you did. We'll see. I'll point it out. I think I know what you did. So first I want to find my net torque. I have 50 newtons. It's applied tangentially. That means that if I have this disc, it's applied at the edge of the disc, and it's also applied perpendicular to the moment arm. So it's 90 degrees between that and the moment arm. So my torque then is going to be 50 newtons. That's the force times the radius, which is 1 meter. So it's 50 newton meters. So my first step, now find my moment of inertia. This is a disk. A merry-go-round is a disk, so it's 1/2 mr squared. You might have made a mistake here. You might have instead did mr squared. Maybe some of you did that. Okay, maybe not. Anyway, this is a disk, so it's 1/2 mr squared. That's 1/2 of the mass, which is 100, times the radius of our disk, which is 1 meter squared. So that's 50 kilogram meter squared. And then I find alpha. That's torque over my moment of inertia. That's 50 over 50 is 1 radian per second squared. And then I use this kinematics equation to find omega after 3 seconds. So omega naught is 0 because it's initially at rest, plus alpha, which is 1, times t, which is 3. So it's 3 radians per second. So A is your right answer there. You could have a multiple choice question, but you'll also have a free response question as well. There are some homework problems that are related to this. Like this number 4 and number 8, or number 7 rather, that are related to this. But let's go back to an old exam. There wasn't a good question on the one in the back of your book, so I'm going to go pull up another exam, and then we'll go to the work energy theorem. So let me look online. We'll find you another exam. Sort of show you some good practice for this. Let's do an old one. Oh. Sorry, give me just a second. Okay, this one's something similar. I have this figure shows, this is follow 7 exam 3. And it says, it has a uniform disk. So again, it's a cylinder that's rotating about its central axis. It has a radius of 10 centimeters. So my radius is 0.1 meters. That's this distance on the disk. It has a mass of 50 grams. It says that in kilograms. I move my decimal place over 3 spots. So it's 50 grams is what? 0.05 kilograms, right? 0.05 kilograms. Um, it's initially at rest, so omega naught is equal to 0. I have 2 forces that are applied, F1 and F2. I know that F1 is 0.4 newtons. I want to know what F2 is. I don't know what F2 is. Um, but I know that at t equal 4.5 seconds, that the angular velocity, omega, is 200 radians per second. It says that it's clockwise, so that tells me that it's positive or negative. Negative, right. So omega is negative 200 radians per second. All right, so this is a very similar problem, but I have to work backwards a little bit. I have this disk. I have two forces. One of them I know the force. The other I don't know the force. Um, but I know that it has, and I can figure out its moment of inertia. Let's go ahead and figure out its moment of inertia. It's going to be 1/2 mr squared. I get that from my table. That's 1/2 of m, which is 0.05, times 0.1 squared. So what's that? 0.025 times 0.01, 0.0025. Is that right? I get that right? I'm pretty sure that's right. Yes, that's okay. All right. So that's my moment of inertia. Now, I know that the torque is I times alpha, and I know I now, but I don't know the total torque, and I don't know alpha. And in fact, I can't find the total torque because I don't know what F2 is. So in order to find F2, I need to know the total torque, the net torque. So now I'm going to set about to find alpha. Now, I do know the the final and the initial velocity and the time. So that should key off on me that I can use my kinematics equations, omega equals omega naught plus alpha times t, in order to find the angular acceleration. So here alpha be omega minus omega naught over t. That's negative 200 minus 0 over t, which was 4.5 seconds. What is that? All right, I'll say negative 44. That's in radians per second squared. Everything's been in SI units, so I have radians per second squared. Now I can find the net torque. So I can take this, and I can take this, and plug it in here. My I, my alpha, 0.0025 times negative 44. Or did I miss a 0 there? Okay, I'm sorry. And so what is this going to be? Point 0.011? Point 0.10? 1011. Negative, right. And that's in Newton meters. All right, so now that I know the torque, now I can work, I'm sort of working backwards. Very similar problem we did before, but I'm working backwards to get what I needed before. So now I know the torque, and I know one of the forces. I'll do this over here so y'all can see in the back. The sum of the torques is going to equal to F1 times R plus F2 times R. One of these is negative. Which is it, F1 or F2? The torque by F1 or F2? Right, so the one that makes clockwise motion, and that's going to be F1, so this is going to be negative. I know that my net torque is negative 0.011. That's equal to F1, which is zero point 0.4 newtons, times R, which is 0.1 meter. That's negative, plus F2 times 0.1 meter. And then I solve that for F2. I'm not going to do it, but you solve it for F2, whatever it is. So that's a very similar problem to the one we worked before, but as I said, we have to work backwards just because of the information that we have. But I'm still finding the net torque, and then using that to, or I found my angular acceleration, then I calculated my net torque, I had my moment of inertia, and then I worked backwards to figure out the force that's actually causing that net torque. Could see a problem like this on the test. Like, as I said, as I look back, I haven't posed these kinds of problems very often, but you should be prepared for something like that on the test. I could do that, you think? I gave it to you today? Yes? Maybe? All right, there's some practice in the homework, and look back at the old exams as well. But you use the same procedure on all of them. It's not really quite as complicated as what we had in Chapter 4 with the inclined planes and sort of all the different forces that are at play, largely because we're simply dealing in rotational motion, so we're not dealing with all the trig that we had before. All right, last part of this is the work energy theorem. We've already seen that the kinetic energy of a rotating body is 1/2 I omega squared. And we sort of use this definition of kinetic energy to create our definition for moments of inertia. So we've already seen this a little bit. Remember that this is a lot like kinetic energy that we saw before, 1/2 mv squared, except now instead of m for inertia, we have I for moment of inertia, and instead of v for velocity, we have omega for angular velocity. So it's a lot similar, works in a lot the same way. It has the same units, which are joules. And the work energy theorem also applies here. That is, if I do work on an object, I will change its energy. In particular, we're just talking now about changing its kinetic energy. So if I have some work that I do on an object, I'll change its energy. So for example, let's say that I have a rotating object. I have a thin hoop that is rotating at 10 radians per second. And I want to know how much energy or how much work is required to stop it. The work required to stop it will be equal to the energy that it has. So I would find the moment of inertia of the hoop, which is mr squared. That's on my table. That's a mass of 1 kilogram, a radius of 1 meter squared. So it has a 1 kilogram meter squared. And then the kinetic energy is going to be 1/2 I omega squared. So that's 1/2 of I, which is 1. And omega is going at 10 radians per second. So it requires 50 joules to stop, 50 joules of energy to stop it. And then if I wanted to stop it in 5 seconds, I can also calculate the power rather that's expended. How is power related to work? Right, it's by the time. So the power is just work or energy per time. So my power is work or energy over time. It's going to be 50 joules over 5 seconds, which is 10 joules per second, or 10 watts. I have an example here for you to work through. Yeah, we might not finish this, but we can finish it up next time. So here I have a big flywheel. I don't know what a flywheel is. Like in an engine, you have flywheels to help transfer momentum from one part to another. A flywheel is just a big spinning disc. All right, so it's a cylinder that's rotating. It's like a merry-go-round. And we'll see flywheels come up in some of our problems. But here we have these huge solid flywheels. They have a big mass and a big radius. They have a radius of like 1 meter, so they're about this tall. Big metal disc about this tall and all the way around. They have big mass, 33,000 kilograms, and they ride on shafts that are 21 centimeters in diameter. These shafts have a frictional force that are acting on them. I'm sorry, this isn't an energy problem. No, this is going back to our torques problem, but that's okay. This is a good problem to work through. So I have this big disc. It rides on a shaft, that shaft has a frictional force, Fk, that acts upon it. You'll follow what we're thinking about here. Have this big thing that's turning. There's a little shaft in the middle that has a much smaller radius, and there's a force that's acting on that. That force is going to cause this big disk to slow down a little bit. So we want to know if this thing is going at a rotation rate of 420 revolutions per minute, how long does it take for this little force, this frictional force, to cause it to come to a complete rest? So similar process that we had before when we were dealing with torques. We want to first find the net torque, find the moment of inertia, and then find the acceleration, and then from there we can figure out how long it takes to stop. So first find the net torque, find the moment of inertia, and then find alpha. All right, so our net torque, I have a force, and I have a moment arm that it's acting upon. So my net torque is F times R times sine of theta. But here my theta is 90, so I'll just leave that out. That's equal to 1. My force is 28 kilonewtons. That's 28,000 newtons. Times my moment arm, which is 0.21 meters. Then you'll find your moment of inertia. Then you'll find your alpha. What's that torque? 28,000 times 0.21. Oh, you're right. Was that a diameter? Yeah. So you're right. 0.21 divided by 2. Do you have that torque then, Lindsay? No. No, that can't be right. 29,000? No. Okay, yeah, too many. 2940. All right, that's in Newton meters. And then let's just find our moment of inertia. So go ahead and find the moment of inertia for this, and then we'll wrap up there. Here, I'm just dealing about the moment of inertia, the big thing here. It has a mass, 3.3 times 10 to the 4th, radius of 1.4. What is the moment of inertia of this object? Or how do we find it? Right, this is like we've seen before. It's 1/2 mr squared. And that has a value of what? What is it again? All right, guys, we'll stop there. We'll finish this up next time, but it's a similar, if you want to go and do it, that's fine, but it's very similar to the one we've done before. All right, y'all have a good day. I'll send out that take home today or tomorrow so you can start working on it if you wish to. It's going to make up not an insignificant portion of the test, so take some time and do it well. Have a good day, okay?